Quantum harmonic. Yeah, so this one's going to be purely classical. Hopefully that doesn't dissuade you all about classical harmonic oscillators, but a lot of the techniques still apply and actually are useful for systems of quantum harmonic oscillators as well. Yeah, okay, so why don't we go ahead and get started. So, I'm excited for this one because we're going to be talking about harmonic oscillators, and specifically coupled harmonic oscillators, meaning that the harmonic oscillators talk to each other. So far, I've really only talked about single harmonic oscillators, which might look like some mass connected to a spring, connected to some fixed point, I don't know, some wall. And this mass goes back and forth, but something that we'll be talking about today is coupled harmonic oscillators. So as we'll see, maybe something where I'll have one mass connected to a spring, connected to another mass. So the whole idea of this is we're starting to add what we call degrees of freedom, meaning independent pieces of our system that can move. So this will hopefully introduce some of the machinery that we need to solve a system like this. Specifically, we'll be talking about what are called normal modes and a normal mode decomposition of harmonic systems of coupled harmonic oscillators. And so the great thing about this, as we'll see, is that it's actually pretty straightforward. The whole idea of this normal mode decomposition is relatively straightforward, and as I sort of mentioned here, when we start adding more and more and more and more of these oscillators, we eventually end up at the wave equation. And so we can actually derive the wave equation from just considering harmonic oscillators like this. And actually, as we'll see at the very end, we solve the wave equation in exactly the same way with this normal mode decomposition. It just turns out that in that case, you have an infinite number of normal modes. And so then, of course, won't get into it today, but that leads into Fourier analysis and a lot of very powerful machinery that we can use later on. And sort of as an aside, what I'll be talking about sort of all the way through this is keeping in mind reference frames and symmetries. And at the end, I'll sort of make a comment of how you can see where our current system, which is Galilean relativity, which tells us how to get from one reference frame to another in classical mechanics, how that might break down, and how we'll know that in the future we'll actually need a theory, a more general theory, special relativity in this particular case. But okay, so let's go ahead and start at the beginning. So like I said, I want to talk about systems of coupled harmonic oscillators. So we'll start with pretty much the simplest thing that we can think of, which I drew it on the last page, but it's just two masses. They can be different. We'll call this one M1. We'll call this one M2. And they're connected with some spring, with a spring constant we'll call K. Okay, so the first thing that we always have to do is write down our Newton's second law, or as I'll probably call them from this point forward, our equations of motion, the equations which govern how things move in our system. And so we know that if we have a spring, the force exerted by the spring is going to be equal to minus K times the distance that it's stretched, where we'll define K to be positive, or not K, D. So D is going to be positive if the spring is stretched, and D will be negative if the spring is compressed. Okay, so this equation really only applies to the case where we have a single oscillator. But it applies in this case as well, but the main thing we have to worry about is this sign here. Because as we know from Newton's third law, when this guy is going to feel a force, maybe it'll feel a force this way, this guy is going to feel the same force in the opposite direction, right? There's only two things talking to each other in the system, and so whenever one feels a force, it has to push or pull on the other with the same magnitude in the opposite direction. Okay, so we can go about this. So I'll sort of draw this a bit in a bit different way, of a different way. So I'll call this length. So say this thing feels no force. In this picture here, the force is equal to 0. So nothing is feeling any forces at all. The spring is perfectly happy where it's sitting. We'd say the spring is at its equilibrium position. And so we'll call the distance between the two masses in this case L0, or L0. Now, in the case where the force is not equal to 0, this spring might be stretched, it might be compressed. I'll call it, or I'll just draw it in this case as being stretched. Just because. And I'll call this L. Same spring, same masses, just different length, different distance between them. So this D here is really telling me the distance the spring is stretched from its equilibrium position. So in this case, we could say that D is equal to L minus L0. Right, and this is consistent with this sort of convention here. So that if L is greater than L0, then D is positive. If L is less than L0, then D is negative. Okay, so now we want to write down our equations of motion, the equations which are going to tell us the forces that each of these masses are going to experience. So in this case, we have two different masses, so we have to have two different equations which govern the forces separate, or govern the motion separately. And we'll sort of base it off of this guy, but again, like I said, we have to be careful about this sign here. But we can sort of just think about this physically. So what's going to happen? So in this case, so say I've stretched the spring like I drew in this picture here. We know that M1 is going to feel a force to the right? So this spring is going to want to compress back down to its equilibrium length. So M1 is going to feel some force to the right, whereas M2 is going to feel some force to the left. We know the magnitude is going to be K times D. And so this just gives us our direction. We'll call the right direction positive and the left direction negative. So we can write out the forces pretty easily as just, so the force on 1, again, this one's positive, AD. And then F2 is going to be negative, KD. And you can see this works the other way around. If L was less than L0, meaning this thing is compressed, D is negative, and the mass here is going to feel a push to the left, whereas the mass 2 is going to feel a push to the right. Okay, so now what I want to do is I want to give myself a little bit more space by moving things around a bit. Okay, I'm going to erase some of this stuff. Here. Okay, so now I'm going to call the position of this guy here the absolute position. So I don't know where I'm going to call my origin. Say I call my origin here. But I'll call this guy x1, and this is going to be some function of time. Okay, so this is just the position of mass 1, and this is going to be the position of mass 2, measured relative to wherever I decide to put my origin. Okay, I know that the force is going to be equal to the mass times the acceleration, so the force on 1 is mass 1 times the acceleration of 1, which we know that the acceleration is the second time derivative of the position. And just for the sake of brevity, I'm going to write time derivatives using dots. So x dot is just dx dt. So that's a definition. It just saves a bunch of writing. Okay. So we can do a similar thing for f2. This is just m2x2 double dot. And now we have our two equations. m1 x1 double dot is equal to k times d. And then m2 x2 double dot is equal to minus k times d. Okay, we're getting there, but this still isn't really all that helpful. Because of the fact that we want to solve for x1 and x2, but we really only have things in terms of d, and d is only really in terms of L. But we can sort of get around this because we know that L is going to be the difference between these two positions, no matter what, right? This is just sort of how we defined L to be the difference between the endpoints. So we know that L is equal to x2 minus x1. And I'll again just sort of make a definition here, again call my origin here. And in the case where the system feels no forces, I'm going to call this x1 0 and call this position x2 0. So the 0 just means that that's the case where nothing is feeling any forces. Everything just is sort of boring. So in this case, L0 is given by x2 0 minus x1 0. And so I now have a sort of messy set of equations, which I can write as, this is k times x2 minus x1 minus x2 naught minus x1 naught, and then m2 x2 double dot equal to k, or minus k, sorry, minus k times the same thing, x1 minus x2 naught minus x1 naught. Okay, we're at the home stretch. And really the only thing that's annoying right now are these terms here, right? These sort of just arbitrary offsets that tell us when this thing isn't feeling any forces. So let's go ahead and figure out what these are. So we know that in this case, it feels nothing feels any force, right? So I might be able to say that x double dot I 0 equals 0. So I is just either 1 or 2. which is easy enough to solve, and this tells me that xi0 is equal to, I'll call this yi0 plus v times t. And this is exactly what we would expect. We'd expect that the position for something not feeling any forces to just be some time-independent offset plus its velocity times time. Okay? Now notice that for f to be 0, v has to be the same. Has to be the same for 1 and 2. So otherwise, if mass 2 is traveling faster than mass 1, then obviously the spring is gonna stretch, and you're gonna start feeling forces. So this v is the same between x1 and x2. That's why I wrote it as xi in this case. We also know that the equilibrium length is fixed by L naught. And so this just tells me that the offset of the second mass, which I'll call y20, is going to be the offset of the first mass plus L0. Okay? So, in this case, I'll just define y10 as y0, and so then that tells me that y20 is just y0 plus L0. So now I have these expressions for x2, 0, or I guess I'll write it as x1, 0. And remember, these can be functions of time. These equilibrium points can move in time. They just have to move at a constant velocity. This one is y0 plus vt, and x2, 0, t is y0 plus L0 plus v. Okay, so this seems like a whole lot of work and not a whole lot of solving the system. But there is a reason why I want to do this. And it's so that I can make some definition, right? So you can see that in each of these equations, I can always pair up x2 and x1, 0. So they always show up as x2 minus x2, 0, x1 minus x1, 0. Where this is just this is the displacement from equilibrium, right? So x1 minus x1, 0 just tells me how far away from x1 or x1, 0 that x1 is. So that's just my displacement from where the mass wants to sit at equilibrium. So I'm just going to define some delta I t, which is equal to xi minus, and these are functions of time, minus xi0 of t, where this is the displacement of mass I. So, when we do this, well, we know that the second derivative of this guy vanishes, because there's no acceleration on the equilibrium points. So we know that delta I double dot is equal to xi double dot, which means that the left-hand side of my equations aren't really affected, whereas the right-hand sides simplify a lot. And so I can end up writing these as m1 delta 1 double dot is equal to minus k times delta 1 minus delta 2, and then m2 delta 2 double dot minus k delta 2 minus delta 1. You can see that the forces on each one are still equal opposite, all of that stuff. It's just now things are far simpler, so now we can solve for delta instead of having to deal with all of these weird offsets and all of this nasty stuff. And then at the end of the day, if we want to find the absolute position, we just plug back in our offsets, which we already found out. Okay? Now, just as a bit of a side note, we could have known immediately that we could do this, because of the fact that these equations here are symmetric, specifically symmetric under Galilean transformations, where a Galilean transformation is just one where I shift some velocity, or all of the velocities in my system, by some constant velocity u. And also by translations in x, where x prime is equal to x plus a. And that's all I've done here. All I've done, all this definition of delta is just a way of shifting into the reference frame where my total system is not moving, and then subtracting off any translational offsets I might have. So that's all we're doing. We're essentially abusing the symmetry of our equations of motion to simplify the form of the equation. And then, of course, at the end, we can just put back those factors in because, of course, everything is symmetric, so it's not going to change the physics. Okay, so these are our equations that we want to solve. Now, this is a bit tricky because of the fact that these differential equations are coupled. Coupled differential equations, which makes them much trickier to solve, just because of the fact that any influence of or influences from this equation are going to show up in this equation, and vice versa. So how are we going to approach this? Well, as a first note, we see that we have two second-order differential equations, meaning two differential equations with at most two time derivatives. So we have two second-order diff EQs. Whoops. EQs. Each order tells me that I need an extra boundary condition. And so, since I have two second-order equations, at the end of the day, I should have to specify 4 boundary conditions. A sort of naive way of thinking about this is just, to solve anything, I would need to integrate 4 different times, and so I'd have to have some constant of integration every time I do that. Now, this will come in handy to remember later on when we have actually found a solution, because we should expect 4 unknowns, 4 free parameters, which we have to then fix with these boundary conditions. Okay, so coupled system of equations. How do we deal with this? Well, instead of trying to brute force our way through this, let's just try to guess. That's actually a very valid way of solving differential equations. Just guess the answer, and see if you're right. In this particular case, we know that this is describing harmonic oscillators, which means that there should be some sort of oscillation, right? So we might guess the solution. And in particular, to simplify everything as much as we can, we'll even go so far as to guessing that all of the masses in our system oscillate at the same frequency. Obviously, this isn't always going to be the case, but it's a particular simple case that we can look at. So we'll just guess some delta I of t, which is ai cosine omega t plus bi sine omega t. Right, so we have 4 boundary conditions. We have 5 unknowns, right? We have a1, a2, b1, b2, and then omega. But we'll see that we can end up fixing a lot of these just by looking at our equations of motion. Okay, so when we plug this in, we find something that looks like m1 omega squared a cosine omega t, this should be a1, plus b1 sine omega t is equal to minus k a1 minus a2 cosine omega t minus k b1 minus b2 sine omega t. I'm going to move this so that you can see it better. And then a similar equation where I just exchange 1 and 2. So, now this is nice because we know that this has to be satisfied for all times, every time. So for any value of t, this has to be satisfied. So we can actually split up all of the terms with cosines in them. So we can pick out the cosine terms. Out cosine by looking at when omega t equals 0, right? Because in that case, all of our cosines go to 1 and all of our sines drop out. And then we can also pick out just the sines by just considering when omega t is pi over 2. And of course here, all of our cosines will drop out, but we'll keep our sines. This is actually a very neat trick, and actually there's a bit of a deeper reason why you can do this with sines and cosines, but this is a really good way of thinking about it for right now. So when we do this, we get a few pretty simple equations. Just m1 omega squared a1 is equal to minus k a1 minus a2, and then minus m2 omega squared a2 equals minus k a2 minus a1, and then minus m2 omega squared, should be 1 omega squared b1 equal to minus k b1 minus b2. And then same thing here, but with b. It's k b2 minus b1. Okay, so we have a set of 4 equations. We have 5 unknowns. 5 unknowns, which are going to be A1, B1, A2, B2, and omega. So we can't solve everything exactly, but we've done something pretty cool, which is we've turned our coupled differential equations into a set of algebraic equations. And algebraic equations are going to be significantly easier to solve than differential equations. So without boring you too much with the actual math of just cranking through and solving these equations, it turns out that there's extra sort of redundancies in this, so we can't even solve for 4 of our unknowns from this. But what we can do is we can solve for either A1 or A2, B1 or B2, and omega. So we can fix 3 things at least. And we do this, when we do this, we get 2 solutions. 2 solutions. The first is that A1 is equal to A2, A2, B1 equals B2, and omega squared is equal to 0. And then our second equation is A1 equals minus M1 over M2 A2. B1 equals minus M1 over M2 B2. And then omega squared equals K times M1 plus M2 divided by M1 M2. Excellent. So what I'm going to do is I'm just going to put sort of, I'm going to put extra little scripts in parentheses in the top of this, just so we know which of these solutions each of these constants corresponds to. And actually, since this omega is 0, I'm just going to call this omega squared in this particular case. So now this gives us 2 solutions, right? So the first solution, which I'll call delta 1 of t, it's a bit boring. This is just A1 1, and delta 2 1 of t is also equal to A1 1. So this is just equal to, I just shift them by some offset, which is the same for both of them, and nothing interesting ever happens. Yeah, so omega being 0 isn't really weird, right? It just means that things aren't gonna oscillate, right? It just means that I've shifted my system and not stretched anything, not compressed anything, and so this is sort of the boring situation. And then the more interesting situation is the one where I have delta 2 1 of t equals A1 2 cosine omega t. Remember, omega is just this thing, so omega is the square root of this, plus b b1 2 sine of omega t. Oh, can't we eliminate the boring as a trivial solution of the... Yes, we can. We can, of course, eliminate that as a boring solution to the equations, but I want to keep it for now. Because of the fact that it serves as an example for a more complicated case later on. So I'm keeping hold of it for now. I mean, it's also as we'll see, this is something we've already taken into account, right? We've already talked about the fact that this system can just be translated by a total amount. And so what I'll end up doing later on is just absorbing it into that constant that we've already discussed. Okay, so now we're almost there. We're almost to the finish line here. So something that I mentioned very early on is that derivatives are differential or linear operators. They're also differential operators, but they're linear operators. Which, just as a refresher, if I have some sum of functions, g of t, and I guess if these are also multiplied by some constants, this is d f dt plus b dg dt. So, what this means is that if I were to add these two solutions, say for delta 1, so say I add both of the, and there's a similar solution for delta 2 to t. So now say I add delta 1, delta 1 1, and delta 1 2. And then I plug this into the equations of motion. If I do that, I'll get something which looks like d2 dt squared, so this is m1, delta 1 1 plus delta 1 2, which, as I said, that's just going to be the second derivative of each of these guys. So m1 delta 1 1 double dot plus m1 delta 1 2 double dot. But remember, I have to also add everything on the right-hand side, which is going to look something like delta 1 1 plus delta 1 2 minus delta 2 1 minus delta 2 2, which then I can simplify, well, not really simplify, but rewrite delta 2 1 minus k delta 1 2 minus delta 2 2. Okay, but we know that, use a different color, this and this satisfy the equations of motion. So this is true with just these pieces, and this is true with just these pieces. So we know that this whole equation has to also be true. So what we found is that a sum of solutions to our equations of motion is also a solution to the equation of motion. So in this case, I can write a more general solution as delta 1. I'll just call this total delta 1, which is going to be a1 1 plus a1 2 cosine omega t plus b1 2 sine omega t, and delta 2 t equals a2 1 a2 2 cosine omega t plus b2 2 sine omega t. So these are my solutions. So to see it more generally, we have to look at our full solution, which is going to be in terms of x1 and x2, which we know we can just write as this should be delta 1 plus x1 0 and x2 equals delta x2 plus x2, 0. If we remember, x1, 0 is just some initial offset, y0, plus vt. x2, 0 is that same offset plus the equilibrium length of our system, plus vt. Now, like I said, this is just some constant offset. So I'm going to actually just absorb it into... Oh, sorry, I forgot to actually plug in the correct solutions of this. So this should be minus m1 over m2, 1, minus m1 over m2, b1. Sorry. So, yeah, as I was saying, we have these guys, which are just offsets, and so I'm just going to absorb them into y0. It's just some total distance offset, so I'll just give it a new name. And sort of putting all this together, I get my final equations, and I'm just going to rename the a12 and b12 to just a1 and b2. Just again to sort of cut down the messiness of the solution. And then plus my offset, plus this constant velocity piece. And then delta 2 of t is similar, m1 over m2, cosine, oh, forgot my constant, cosine omega t, and these should be x1 and x2, sorry. x1, x2, plus, minus m1 over m2, b1 sine omega t, plus y0, plus L0, plus vt. And just as we expected, at the end of the day, we have 4 unknowns, which can be fixed by the 4 boundary conditions we need for the differential equation. Our unknowns being, do this in blue, a1, b1, y0, and b. L0's not going to be a free parameter because that's just a part of our system. Same with the masses and omega, which is, I'll just write it out again as k times m1 plus m2 over m1, m2. Okay, so what does this look like? Well, I mean, it's always good to make sure that when we come up with an answer like this, that it's making some physical sense. So when we do this, of course, if we don't offset anything by any equilibriums or give it any velocities or anything like that, it's just gonna sit there and be boring the entire time. Now, if we were to shift, say, just the velocity, give me 1 second, I'm gonna rerun this real quick. So yeah, so say we offset everything by the same amount. Again, obviously nothing interesting happens, so that's good. That's something that we would expect because nothing feels any forces still because we haven't compressed or extended the spring. Now similarly, if we just give everything the same velocity, nothing really happens because everything's just moving with some constant velocity together. But if I were to offset one of my masses relative to the other, we see some oscillations start to form, and even ramp them up by increasing the initial displacement. So that's good. We can see that now if we give everything a total velocity shift, it just oscillates while moving. Again, that looks like what we would expect. And then we can also see that if we just kick, say, the second mass a little bit harder than the first mass. So the second mass has a higher initial velocity than the second. Then it's still going to oscillate, right? Because like I said, if one of them has a higher velocity than the other, then the spring's going to end up stretching or compressing. Now note, all of these constants were fixed by just specifying the boundary conditions of the system, which is, what we would sort of hope to happen. So I'm actually going to pause this, that nothing ends up crashing on me. So this is the solution to the system. We've just found the different. I'll write this out. So our step one was guess the solution, where everything, all masses oscillated with the same frequency. We solve our EOM, our equations of motion, for the different possible omega, along with the relations between coefficients between our A's and B's. And then 3, we just we summed the different resulting solutions to get a general solution. And this is all the normal mode expansion is. It's just doing this process. And then, of course, we fix all of the leftover constants with boundary conditions. And it turns out that we'll do another example of this, a bit more interesting one. But it turns out that this never gets conceptually more difficult. I can add, 10, 20, 500 different masses on the springs. You always just do this. You just guess the solutions where everything oscillates with the same frequency. You solve the equations of motion. You get the algebraic equation. And you find all of your possible omegas. And then you sum all of these possible results, which then leaves you with coefficients you can fix using boundary conditions. And that's all there is to normal mode expansions. Nothing too mysterious like that. And like I said, conceptually it never gets difficult. You just have more and more tedious math as you go to more of these, more oscillators. But, computers are great at solving systems of equations, algebraic systems of equations like this. So, to all intents and purposes, with this method, we've solved every system of coupled harmonic oscillators, essentially, for any set of boundary conditions. It's pretty cool. So I'm gonna take a little bit of a breather, give you guys a chance to ask any questions you might want to ask. And then we'll move on to a slightly more interesting case. Yeah, so this trivial solution that we found, yeah, it was boring in this case, but in general, we don't find a trivial solution like that. All of our solutions are, in general, are non-trivial, and so we have to always take them all into account. What case? So we're not going to go up to n masses quite yet, just because I mean we've like I said, there's not really much more conceptually complicated about going up to n masses, but yeah, the only case of having n masses is more annoying, tedious algebraic system of equations. So the next one we'll do will actually just be another 2-mass case, but slightly more interesting dynamics. So, you said that this was the solution for the system. Is it somehow obvious that there can be no others? Yeah, I mean, we have at the end of the day, we have only specified 4 boundary conditions, right? Because we had 2 second-order differential equations, and when we have this general solution, we have 4 constants that need to be fixed, 4 independent constants that need to be fixed. So at the end of the day, this solution will satisfy any set of 4 boundary conditions that I give it. It'll also satisfy the equations of motion. And I believe there's a theorem in solving differential equations. I don't quite know how to prove it, but if you have a solution which solves your differential equation with the given boundary conditions, then it is the solution, the unique solution. Like I said, I'm not 100% sure how it's proven, but I'm pretty sure that that's a hard mathematical fact. Hopefully that satisfies the question. Yeah, I don't know the name of the theorem. It's just yeah, math facts. That's sort of the the physicist. Yeah, it's the unique solution, I promise. But I'm sure that, yeah, I'll write it out. We have people saying in chat that this is the card Lindelof theorem. I don't know if that's 100% correct, but I'm trusting you on that. You probably know it better than I do. Alrighty. Alright, bye Narf. Thanks for coming. Appreciate it. Alrighty, so if there aren't any other questions, let's move on to this other case. So, yeah, the last case was a bit boring, but let's try a different one. In this case, we'll add a couple of fixed pieces, which I'll have as blue, and we'll again consider 2 masses, which I'll show as red, and connect each of these masses not only to each other, but to the fixed points. So these are fixed. So these guys aren't going to move. They're just going to sit there, and obviously they're going to feel a force, but the force isn't going to influence them. In some case, we can think of these as having masses which are infinite, so they're never going to accelerate. So, since these are fixed, we don't really have to worry about their dynamics. Yeah, okay, I'll represent them as a wall. That's probably a better idea. Yeah, something like that. How about? Okay, so these walls are fixed, the masses aren't, and so we'll do a similar thing, where in this case, I'll consider all of the springs to be the same, and both of the masses to have the same mass. Just for the sake of simplicity, it'll cut down on the how atrocious our equations look. Okay, so now I could, in the same way, start by describing these by some x1 of t, x2 of t, describe their equilibrium positions, which might be x1 0, x2 0, whatever. But why go through the same nonsense again? We already know that we can, as long as we're in the rest frame of this system, right? The system isn't moving with some constant velocity. I can always subtract off constant shifts. So I'm just going to describe these again by their displacements. I'll call delta 1 and delta 2. So the displacement from equilibrium, from where these masses want to sit if nothing feels forces. Okay, so again, we just have to write down our equations of motion, which we can see by, or I'll just write this as m delta 1 double dot. That's our acceleration. So we're going to get the same term for the force between these guys from this spring. So I'll just write that out, minus k delta 1 minus delta 2. But mass 1 here is going to feel an extra force from this spring. And so we know that's going to be proportional to the displacement, proportionality given by k, but what's the sign? And that's pretty straightforward to figure out. Just thinking if we shift the mass to the right a little bit, what direction is the force that this feels from just this spring? That's going to the left. So if delta 1 is positive going to the right, the force is going to be negative. So we know that it's going to be something like that. And we have a similar story for delta 2, where we have the equal and opposite force. And then again, if I push mass 2 to the right, it's going to compress this spring, and so the spring's going to push back to the left. So it's going to feel a negative force with a positive displacement. So I know that the equations of motion have to look like that. So again, we just do the same thing that we did before. We guess our solutions. Delta I equals AI cosine omega t plus BI sine omega t. And we just plug this in. And we get two equations, which look like A1 cosine omega t plus B1 sine omega t equals minus k times 2A1. The 2 coming from both this guy and this guy, minus A2 cosine omega t minus k to b1 minus b2. I'm running out of room. Sine omega t. And of course the same thing for just exchanging ones and twos. So again, I separate things out into sines and cosines. solve the algebraic equation. Again, I won't put you through the headache of showing you that. It's easy enough to plug into a computer. You go to Wolfram Alpha, plug in the system of equations, and it'll spit out a solution for you. And we again get two solutions. You might notice a theme while doing this. If you maybe look at 3, 4, whatever, however many of these you look at, you'll always get the same number of solutions as degrees of freedom in your system, which is good, because that contributes to this fact that we can sum the solutions together and get a general result. Maybe I'll explain that a bit more when I'm done with this problem, if you guys want. So I have two different solutions in this case that look, they look somewhat similar to the other. Whoops, that should be 1. This should be 1, 1, 1, and then omega 1 squared equals k over m. So you see now this one is no longer trivial. It's no longer a trivial solution, and so it's important to keep in mind equals minus a1 2 b2 minus b1 2, and then omega squared 2 is equal to 3k over m. So again, we just plug this in. Delta, oh, that's a terrible delta. Delta 1 of t is then going to be equal to a1 1 cosine omega 1 t plus a1 2 cosine omega 2 t 1 b1 1 sine omega 1 t b1 2 sine omega 2 t, and then we have minus a1 1 omega 1 t should be plus. You're asking the question that I want you to be asking. That's a great question. I'll get to it in just a moment. b1 1 sine omega 1 t minus b1 2 sine omega, whoa, what is that? Omega 2t. So these are our solutions, and these are our general solutions. Notice we have 4 free parameters to be fixed by 4 boundary conditions. Now, Rodrigo asked a fantastic question, which is there's no solutions where the masses are at rest. Well, so the solution where the masses are at rest are just the ones where I never displace anything, where all of these constants are just 0. But I think what we're getting at is again this idea of going back to x1 and x2 like we did before. Right, I have x1, which is delta 1 of t, so this whole mess plus whatever y0 is plus vt, and then x2 of t delta 2 of t plus y naught plus L naught plus Vt. Hold on. Haven't we introduced two more free parameters? Did everything break because we were working in specifically the rest frame of the system? And so now we can't solve this in a general reference frame? What's going on here? And actually, that I'm curious if you guys have any answers. You guys might have any ideas of what's happening here. So the problem is that we when we go to a general reference frame, we get 6 free parameters. And we still have only written down 2 equations of motion, second order differential equations, which only give me 4 boundary conditions. So the whole system is underdetermined. Am I screwed? Do I have any way out of this? I'm curious if anyone has an idea of what's going on. And I'll give you a hint. What did we assume about our system? What assumptions did we make when we were starting out with the system? Ah, yes, you're on the exact track. So we assumed that these walls were fixed, right? That's exactly what we assumed. So if yeah, perfect. If we're running alongside this, right? So if this is us trying to make measurements about the system, and we're running alongside this with some velocity v, yeah, we're going to see this entire system moving to the left with velocity v. But if we describe the walls by some other coordinate, I don't know, call them x3 and x4, we just know that these never experience any acceleration, which means that these can certainly have some offset, I don't know, y3 plus vt. And of course, we know that x4 is going to be related plus, I think, 3L naught vt. And there we go. We have our extra constraints to plug into the equation, the velocities of the walls and the offsets of the walls. So we actually never run into problems because we, at the end of the day, do actually secretly have 6 constraints. We just made a assumption at the beginning that everything was being held fixed. Basically, we assumed at the beginning that we were always in the rest frame of the system, or always in the rest frame, system. Okay, so what all does this look like? Pull up my nifty little animations here. So we have 2 normal modes. And these normal modes, if I give these some initial displacement, are going to look like this. So we have one slow mode, which is the lower one, which is just the 2 oscillators, essentially the case where I never extend or compress the middle spring. And then I have a fast oscillating mode, which is essentially the two oscillators, as we say, they're always oscillating out of phase. So one's always going in the complete opposite direction as the other. And so these are just the two normal modes, as we call them. So now I can have some fun and go ahead and, play with the offsets of these, and I can mess around with what I want my initial conditions to be, and this sum of normal modes gives me any solution that I could want, because I have the exact number of boundary conditions as free parameters to fix. So this is the general solution. Okay, so I think again I'm going to take a quick break, see if there's any questions. Okay, have some. Would there be more modes with different constants, i.e. if the spring constants are different? Imagine masses should go in and out of phase then. Oh, so no, so if we had different constants, so if we had like different masses, different spring constants, we would still get only two normal modes. The expressions of the frequencies would just be more complicated. So again, if I go up here, you can see that we still found just the two normal modes here, but the expression of the frequency was a bit more complicated. And it's the same situation here. But at the end of the day, it's just, again, more tedious algebra and messier equations that sort of obstruct the point. But yeah, you can plug in, different masses, different spring constants, whatever you might want. You'll still only have two, as many solutions or as many normal modes as independent free parameters, or or not independent free parameters. The word I'm looking for, completely blanking on the word, but the independent things in your system that can move. So just as if people have other questions, go ahead and ask them. The reason that this whole story works, and this whole the whole reason why we get the same number of solutions as things in our system, or independent moving things in our system, for some reason, degrees of freedom, there we go, that's what I'm looking for, along with the origin of the name normal modes, is we can essentially think of think of an XY axis. XY. I know that I can write, or I guess this is just think of the plane. Thanks for telling me it was degrees of freedom. I completely blanked on that one. So I'm trying to parameterize the plane. I can do that with two orthogonal vectors, or as we would say, normal vectors. They're normal to each other, which I can call x hat and y hat. So it actually turns out to be the exact same thing. In this case, right, where I have these two solutions, right? I have the solution for x1, or for mass 1, and the solution for mass 2. So if I take all of the possible solutions for that, I I should be able to decompose it into a basis not unlike this. And so that's all we're really doing. And so then our exact solution, or our general solution, is essentially, you can think of it as just some vector in the function space, in the space of all functions. Now, so that's where the name normal modes comes from. Is these are essentially orthogonal, in a very similar way that these two things are orthogonal. The normal states are equilibrium states, right? So that sort of depends on what you mean. So equilibrium states, I think it sort of comes down to semantics. I think I get what you're asking. So the normal modes, it's not necessarily that, I run this for some time and everything's going to end up being in its normal modes. That's not actually the case, unless I have maybe some damping going on. But in the case where I have no damping, let these things oscillate for however long, a general solution will look nothing like the normal mode states, actually. It's just that the normal mode states are the states which form essentially this basis of orthogonal states in our space of functions, our space of possible solutions. And just the reason why they're special is that they're all of the states where everything oscillates at the same frequency. I hope that clears up that question. Another thing to be careful about is, when we talk about equilibrium with harmonic oscillators, we typically mean, the state where nothing is moving, nothing is feeling any forces. But I think the question makes sense. Okay. Okay, so now let's go on to the point that I think people have been sort of waiting for, which is let's go crazy. So as I said, this whole normal mode business works for any number of things, any number of independent oscillators that I want to put in. Now, keeping in mind these are simple harmonic oscillators, so no damping, any of that. But I can essentially have any number of simple harmonic oscillators. I get this set of algebraic equations, I plug them into my computer, and I find a solution. So let's go crazy. Let's take the case. Let's look at the case where we take n to infinity. So what happens when we take n to infinity? Okay, so again, let's just keep things simple, work in the rest frame of the system, only talk about displacements. Furthermore, it's going to get a little overwhelming if we're always thinking about an infinite number of oscillators. So we'll just look in some neighborhood. So we'll take like 3 masses, which I'll draw like this. And just the dots means that, this keeps on going and going and going. Again, to keep our lives easier, we'll assume that these are all the same. All the masses are identical, all the springs are identical, all that good stuff. But again, this just keeps life easy for us. And now I'm going to call the equilibrium positions, so I'll draw these sort of offset from the locations of the masses. I'll call this x minus L naught. I'll call this x, and I'll call this x plus L naught. Now the actual location is going to be given by our deltas, which I can write like this. It might already be a little bit suggestive that I'm using a function notation for it. But at the end of the day, this is the same thing as what we were doing before, except saying 1, 2, 3, we're centering everything at some value x. So now it's just writing down the equations of motion. We'll say m delta double dot, specifically the equations of motion for this guy. Delta double dot x. There's also a t hiding in here, but I'm gonna suppress it for now, just again to keep things from blowing up and being too confusing. And so sort of by the same logic as before, we can find that this is going to be delta x minus delta x minus L naught. Right, so the force on this spring is the force on this spring here is how much it's extended or compressed, and it's always going to push against the displacement of x. And the same thing here. So I get k delta x minus delta x plus L naught, which I'll just write a little bit more compactly. We'll just write this in terms of delta double dot at x. This is minus k over m times 2 delta x minus delta x minus L naught minus delta x plus L naught. Okay, so now, as a terrible pun, we're going to take a quick mathematical tangent to remember our definition of the derivative. Specifically, if I have some f of x, then the derivative evaluated at x is going to be the limit as h goes to 0 of f of x plus h minus f of x divided by h, which I'm going to call capital F of x. So if I want to take a second derivative, say, just for the fun of it, that's going to be taking the derivative of big F, which is d2f dx squared, evaluated at x. And this is, of course, going to be the limit as h goes to 0 of big F of x minus, big F of x plus h minus big F of x divided by h. Need a new line for this, which, once I expand this out, remember, for this guy, I just take f of x, which is defined up here, and wherever I have an x, I plug in x plus h, and then I just subtract off whatever f of x is. So this is the limit as h goes to 0 of, I get f of x plus h, oh, that's little f, sorry, little f minus, right, coming from this term with x plus h plugged in for x, f of x plus h, and then minus f of x plus h plus f of x, is this minus sign here, all divided by h squared. Just get an h times an h, which I'll rewrite. And I'm gonna shift my where I'm centering this at, just for simplicity's sake. So I'm gonna shift x to x minus h. At the end of the day, it doesn't matter because I'm taking the limit as h goes to 0 anyway, so it's not going to affect anything on the left-hand side, but it does make things over here a bit simpler, and I get something which is x plus h minus 2f of x plus f of x minus h over h squared. Well, this looks pretty familiar here, in that it's almost the numerator is almost exactly what we have up here. All we need to do is to have an extra factor of L naught in the denominator. So let's just multiply this by a fancy factor of 1. So this second time derivative is going to be equal to k L naught squared over m, delta of x plus L naught minus 2 delta x plus f of x minus L naught divided by L naught squared. Okay, this is pretty cool. We're getting somewhere with this. But the problem is, if I just try to naively take the limit as L naught goes to 0, I run into a bit of a problem. Yeah, this part looks like a derivative, but I also have an L naught there, so I get some 0 times 0 divided by 0. Like, things are getting a little bit ill-defined, it seems. But also, if we think about this physically, if I try to take L naught to 0, I'm trying to cram a whole bunch of masses right on top of each other. And in particular, I'm trying to cram an infinite number of masses into an infinitesimally small region of space. Obviously, we're not dealing with gravity or anything like that, but something that still seems not great to do. So what we should also be doing is, along with taking L naught to 0, we should also be taking m to 0, but in a way to keep things sort of well-defined. So how we'll do that is we'll talk in terms of a mass density, a linear mass density in particular, which I'll call rho. And this is going to be big M divided by big L, where big M is the total mass of the system, so this is n times m, and and L is the total length of the system, which is n times L naught. So you can see this is just m over L naught. So if I just fix this rho, this mass density, I fix that to be constant as I take both m and L naught to 0. Everything is nicely defined, at least there. But we also have another problem, in that we don't want the individual masses overlapping, right? So as these things get closer and closer together, you can think of the springs in between them being teeny, teeny, tiny. In which case, to keep everything from overlapping, they need to be incredibly stiff. We need to keep upping the stiffness of these springs. In other words, we need to keep cranking up the spring constant. So another thing that we can talk about is the total stiffness of the system, which I'll call big K, which I'll define as K L naught. So again, this is something that I'm going to fix, keep constant, so that essentially I take little k to infinity as I take L naught to 0, but I do it at the same rate to keep this product fixed. Okay, so I do that, and so then this is quite nice. I'm going to write this on a new page, because my equation of motion simplifies to k over rho times this, delta x plus L naught minus 2 delta x plus delta x minus L naught divided by L naught squared. And now, the moment we've been waiting for, we take n to infinity, we take L naught to 0, right? L naught to 0 implies taking n to infinity, so as this all stays well behaved. Or I guess really so that n times L naught is fixed. So the length of our system remains fixed. And so then this just here becomes a second derivative. So I'll write it as a partial derivative with respect to x. And at the end of the day, I have an equation which looks like d2 delta dt squared is equal to k over rho d2 delta dx squared. Or if I want to call this c squared, c squared, d2 delta dt squared equals c squared, where this is just some constant, d2 delta dx squared. And we have ourselves a wave equation. This is the wave equation for a string. A one-dimensional string. So this in particular describes essentially density perturbations in the string, right? Because we're considering, if I have my string here, I can turn this off. If I have some region of high pressure here, that's the same as essentially compressing springs in that region. So this is sort of this idea that if I have a field, which in this case a string is a field, all it is just an infinite number of coupled harmonic oscillators infinitely close together. That's all it is. So I'm going to take a quick pause here. The last thing I want to do is solve this. There's some discussion going on in the chat, so here's some questions. So this situation looks like a sound wave traveling inside a tube closed on both sides. Yeah, that's basically what we're doing. Yeah, that's actually pretty much exactly what we're doing. And of course, that will obey a wave equation just like this. In this case, we get sound waves traveling in a string. It's a very similar thing. Keeping the total stiffness constant seems kind of arbitrary. Yeah, I mean, it is a bit arbitrary. But the main thing is that we want to keep this whole ratio constant. That's essentially all we're doing, and we're defining these sort of bulk properties to do that. We could have, of course, just, at the beginning said, I don't care what this is, I'm going to absorb the L naughts into this and call this C squared, and just enforce that this whole thing is well behaved. But there's sort of this physical motivation of the fact that, well, I don't want an infinitely dense region I don't want an infinite amount of mass in an infinitesimally small region of space. So I'm going to keep this ratio constant, and then the same reason here is to keep everything from bumping into each other and overlapping. I have to keep cranking up the stiffness of each individual spring, is governed by K. So as I take L naught to 0, K has to go to infinity, and so I'm just going to treat this product as well behaved. That's sort of the, it's obviously not like hard rigor showing that in all these limits all these things are always well behaved, but that's sort of the physicist intuition behind it. Hopefully that makes sense. Okay. I think I want to do one last thing for wrapping up, and that's going to be solving this wave equation, the one-dimensional wave equation, so nothing too crazy. So, how do we do this? This is a second-order partial differential equation, as we would say it. So it might sound a bit scary to do that, but it's not too bad. Particularly this one isn't too bad. And the way that we'll go about solving it is essentially the same thing as we did before, which is guessing the form of the solution. In particular, we're going to guess that delta of x and t is just some function of x times a function of t. We don't know what x and t are, but we know that big X only depends on x, and big T only depends on t. So that when I take these derivatives, this derivative here is only going to see x, and this derivative here is only going to see t. So when I write this out, I get something like x second derivative on t dt squared is equal to c squared times t of t d to x dx squared. And I'm just going to shuffle things around, and I get something which looks like 1 over t of t d2t dt squared is c squared over x d2x dx squared. Okay, so now here's the trick. Here's the trick of all of this. The left-hand side of this only depends on t, not on x. This side here is the opposite. This only depends on x, not on t. So, if I want to equate these things, and I know, say, I start on the left-hand side, this side can't be a function of x, that means this side can't be a function of x. I know that this side can't be a function of t, which means that this side can't be a function of t, right? That's the whole point of equating two things. And the only way to do that is if both of these sides are equal to the same constant. So I'll write it just for convenience d of t d2t dt squared is equal to minus omega squared 1 over x d2x dx squared is equal to minus k squared, where omega squared is equal to c squared d squared. That's the only way I can satisfy this, is if these are equal to constants. But again, just shuffling these around a little bit, I can see that, so this is d2t dt squared minus omega squared t, and d2x dx squared minus k squared x. But these are just equations for harmonic oscillators, right? That's our solution that we always have for harmonic oscillators. So I know the solution at this point. I know that t of t is going to look something like, I'll use alpha and beta in this case, alpha 1 cosine omega t plus alpha 2 sine omega t, and then x of x is equal to beta 1 cosine ax plus beta 1 sine of kx. Now remember, this isn't my final solution, because my solution I know is the product of these two things, in which case I will use this, as we call it, the dispersion relation. And then I'll also use some trig identities. Again, I don't want to bore you guys with the exact math behind it. Hopefully you trust me, and if not, I would recommend doing it for the practice. This is going to be something like cosine of k x plus ct, a2 cosine k x minus ct, plus b1 sine of k x plus ct, plus b2 sine of k x minus ct. That's our general solution. Well, it's not our general solution, actually. This is one solution, right? This is a solution for a particular value of k. Yeah, this is a particular value of k. In other words, this is a normal mode. Just the same as before, we've solved the equation for a single value of k, but we know that k, from our dispersion relation, we've only fixed omega to be proportional to k. We haven't fixed k, so k can take any value. So in this case, we have to actually sum over our normal modes. In which case, each one of these coefficients can be different for a different k. So in general, I'll write these as functions of k, only k, and you'll see that if I plug in k there, or plug these in as functions of k, that doesn't affect anything because I'm only taking derivatives on x and t. And so summing everything up is just going to be summing over all possible values of momenta, or not over k. It ends up being what we call the wave momentum, but over k. So that is, in this case, just integrating over all possible values of k. So from minus infinity to infinity, a1 k cosine kx plus ct plus a2k cosine k x minus ct plus b1 sine k x plus ct plus b2 k sine k x minus ct. Ooh. Okay. So second simplification would have been easier to show with complex numbers. Yeah. All of this is, it's a lot. It might be easier to look at with complex exponentials, but I figure more people are familiar with sines and cosines, so I try to stick with that. And yeah, this integral looks familiar. Yeah, I mean, if you've seen Fourier, anything having to do with Fourier analysis, then this is going to look very familiar. This is essentially the root of Fourier Fourier analysis. Yeah, so this is just the continuous case of a Fourier transformation. So you might have seen this as a sum over k. This is the case where k can take any value, not just integer values. So basically, we haven't pinned down the endpoints of our string. As soon as we pin down the endpoints of our string, which is probably something I'll look at in the future, you find that k can only take integer values or integer multiples. In which case, it's a discrete sum. It's not a integral like this. But yeah. Okay, so final thing is something special about the one-dimensional wave equation, which is the fact that if you look at this, everything is in terms of either x plus ct or x minus ct. That's the only dependence on x and t that I have. X plus ct or x minus ct. I mean, the integrals don't affect that, right? Because the integrals only ck. So I only have dependencies like x plus ct and x minus ct. So just as sort of a lazy shortcut, I can write something like this, where I might not know what f and g are, but now I just have to specify my boundary conditions, and then I can solve for f and g. So just as a quick example of that, let's say that at t equals 0, this has the form of something like some Gaussian function. So x e to the minus x squared. And then we'll say that I don't push or pull the string anywhere. So d delta dt at t equals 0 is equal to 0. So I'm not pushing on this string at all. I'm just pulling it up into this Gaussian configuration and essentially letting it go, or I'm measuring that it has this configuration at t equals 0. Okay, so this guy here actually ends up being the easier of the two to start with. So d delta dt is going to be whatever I'll say f prime of x plus ct, where the prime just means I'm taking a derivative of the whole argument here. And then this is minus g prime x minus ct. Take this at t equals 0, and I find that f prime of x is equal to g prime of x. Which then I can just integrate to find that g of x is equal to f of x plus a constant. And then I use this guy here, e to the minus alpha x squared is equal to, well, now it's 2 f of x plus my constant. And so I can just set this constant to 0, and f of x is equal to 1/2 e to the minus alpha x squared. So that's f of x, so I know g of x in terms of f of x, and I also know that I can just plug in x plus ct and x minus ct into these into this argument to get my solution. So that's going to look something like x t equal to 1/2 e to the minus alpha x plus ct squared e to the minus alpha x minus ct squared. Okay, this is great. And as we'll see, this corresponds to, this is a left moving wave, and this is a right moving wave. But if we remember, actually, I'll show that just really quick. Yeah. So, yeah, this is all this looks like. I have one piece which is going left, one piece which is going right. They intersect, they interfere constructively, and then they move on their separate ways. That's all this is describing. But, as we discussed at the very beginning, we have to specify our reference frame. Remember, everything having to do with these deltas was done in the rest frame of the system. Meaning that if I have a string, so I have a string, whatever it may look like, I'm not moving relative to this string. I'm sitting here, I can say that this string is stationary, and I see things like delta. So what if I want to move with some velocity v? Well, we know how to do that. We just do a Galilean transformation, right? And all that's doing is to get into this frame, which is moving, I just take all values of x, which are at rest, and I replace them with x plus vt. Right? I'm just shifting my position with some constant velocity. In which case, then these perturbations are going to look something like, well, in this particular case, but I'm going to write it in the more general case, f of x plus vt plus ct plus g x plus vt minus ct. Which again, I'll just rewrite f of x plus c1t plus g of x plus, x minus c2t. For c1, I've defined as c plus v, and c2 is c minus v. So I no longer see the two waves traveling at the same speed. So this is the speed of the waves in the string in the rest frame of the string. As soon as I shift outside of that rest frame, I get this asymmetric picture of what's going on. So again, just to show that, I'll go ahead and shift my velocity up. Oh, that's probably a little too much. So you see that I'll see one wave moving slowly forward. So this is me moving to the right with some velocity. I see one wave creeping forward, whereas the other one's moving much faster to the left. And I can keep going. I can keep increasing my speed to the point where I actually start to see both of the waves traveling to the left. This is just traveling faster than the speed of sound. There's nothing wrong with it. I'm not breaking anything. It's just which reference frame I'm deciding to be in. So now, as sort of a, I guess, spoiler to what we'll find in the future, when we look at electricity and magnetism, we find that light obeys a wave equation. I mean, it looks basically exactly like this, except in 3 spatial dimensions. But the issue is that light does not travel in a medium. There's no string, there's no water, there's no air, there's nothing. It travels in a complete vacuum. This means that there is no rest frame. There's no unique rest frame that I can stand there and say, okay, the vacuum is sitting stationary. The vacuum is not moving. In the same way that I could say it with the string. I could say, okay, I'm holding the string, whatever, I'm standing in front of the string isn't moving, so I know that these waves are going to be traveling symmetrically in either direction. Now with light, you can't do that because there's no unique reference frame where you can say the vacuum is stationary. Everyone sees the vacuum as stationary. So the conclusion is that the speed of light has to travel the same for everyone. So you might ask yourself, well then, okay, if I have a wave equation like this, I mean, I solved it. I solved the wave equation, and I found that when I go to a new reference frame, I get asymmetrically traveling waves. But this new reference frame in special relativity has to also see the speed of light the same as the original one. So the question is, how do we reconcile that? How do we allow both of these things? Well, one answer is, well, okay, there is this ether, this vacuum, or this medium that light actually does travel through that we've just never detected yet. But that's been disproven by lots of different experiments. So the short answer to the story is that we have to change this. We have to change our rules from getting to one reference frame to the other. And that is special relativity. That's all special relativity is. Special relativity is just replacing this rule with something that is consistent with the speed of light being the same in all reference frames. So, with that, I think that's a good place to call it. If people have any closing questions, I'll be more than happy to answer them before I wrap up. Hopefully this was a good one. I was excited for this one. Hopefully you guys found it as exciting as I did. Thank you guys. I appreciate you guys showing up. Yeah, so I'm not seeing any questions. A little bit longer. Alrighty, well, yeah, thanks again for showing up, and if you're watching this later, then, yeah, thanks for your support there. I hope to see you guys next time.